Hello everybody. Let's continue on in chapter 19. Okay, let me kind of remind you where we're at. We've been talking about thermal exchanges between two objects at different temperatures. When we have two objects at different temperatures, like a system and the surroundings, or a rock and a cup of water, the particles in the hotter object, or the hotter part of what we're looking at, are moving faster. And they collide with the cooler, slower moving molecules and atoms. And there's a transfer of kinetic energy and there's a transfer of momentum. So what happens is over time, the hotter object or thing, okay, cools off and the cooler object warms up because there is a flow of energy from hotter to cooler. When they reach the same temperature, we call it thermal equilibrium. Now remember, thermal equilibrium means that the state variables have stopped changing, that everything's got the same average kinetic energy. Now, we've got linguistics problems. Let's think about how we use heat in everyday language. Heat in everyday language would mean, go turn on the heat, or go turn up the heat, or go turn down the heat. We're using the word differently here, okay? Physics use of heat is different. Heat is a process of transferring energy on that atomic level. It's a thermal energy transfer. It's between a system and its surroundings, or object 1 and object 2, and heat transfer happens when we have objects at different temperatures come in contact with each other. Now, temperature is a measure of average thermal energy content, and it's a state variable, okay? So if temperature increases, that means thermal energy had to increase, because for the average to increase, the overall has to increase. Heat then is that energy transfer between a system and its surroundings, or between two objects, due to thermal atomic level interactions. This is essentially collisions on the atomic or molecular level, okay? And heat is not a state variable. Thermal energy is the total kinetic potential energy at the atomic level due to vibrational motion, rotational motion, and translational motion. Now, I threw that word potential energy in here because of vibrational motion. When something is vibrating, remember, the energy is always going back between kinetic and potential, okay? Now, just observing a system tells us nothing about the process by which the energy left or entered the system. We have to do some specific things, okay? Now, the way that energy, remember, moves in and out of the system is heat and work. If you increase the thermal energy of a system, you see an increase in temperature. The more the temperature increases, the more work or heat, well, more work was done on, or heat was transferred into the process, okay? And if the temperature were to decrease, then some work and heat were transferred out. But how much of it is work and how much of it is heat depends on the pathway you take between point A and point B, the two states on a PV diagram. So the process of energy transfer due to temperature differences, heat, always shows a net flow of energy from hot to cold. Remember, I can't put a hot object next to a cold object and have the hot object get hotter and the cold objects get colder. It just doesn't work that way. Hint, we're going to talk about entropy, and that's one of the concepts that's going to be important there. So, just a reminder, quickie, Work is mechanical, heat is thermal. That means work is macro scale, heat is submicroscopic. Work requires a force and a displacement. Heat requires a temperature difference, which means there's different levels of motion on the atomic level. Okay, the micro, macro. Work is positive, a gas is compressed, energy is transferred in. Heat, Q is positive, then the environment was at a higher temperature than the system. And you can read on down there, but just kind of some overviews. Now, for us, remember the unit of energy is going to be the joule. But upon occasion, you're going to find problems that have calories in it. So remember, 1 calorie is 4.186 joules. A food calorie is a calorie with a capital C because it's actually equal to 1,000 normal calories. It's a kcal. And it equals 4,186 joules. Now, recapping the first law of thermodynamics. Energy cannot be created or destroyed, only transferred or transformed. And that means the change in energy of the universe is 0. So any energy gained or lost by a system equals an opposite change in the energy of the surroundings. And we're dealing with processes where the mechanical energy of the system is not going to change. So that any change in energy of our system is going to be manifested as a change in thermal energy, which is going to be due to work external and heat. Now, this is a simplification of the first law of thermodynamics, but it's what we're going to use when we start looking at heat engines. Now, when work is done on or by and heat flows in or out of a system, the thermal energy content changes, but also the pressure, volume, and temperature may change. These 4 things, thermal energy content, pressure, volume, and temperature, are all interrelated. So, I saved that in there. Well, anyway. You can look at page 524 in your textbook, 19.1. It's kind of a diagram like I drew in the last video where we looked at energy in and energy out. So let me just give you a quickie drawing here. So we can have work in, we can have heat in, we can have work out, we can have heat out, and what it's going to do is it's going to go into E thermal. So that energy in is going to go to E thermal, or if it goes out, it's going to come from E thermal. Okay? Now, we're going to talk about 3 special processes. And what's special about these 3 processes is that for each process, one of the 3, change in thermal energy, change in work, or change in heat, is 0. Now, in an isochoric process, work external is 0 because there's no change in volume. So isochoric. Delta V is 0, so work external is 0, so any change in thermal energy is going to be equal to heat. In an isothermal process, change in temperature is 0. Which means that the change in thermal energy is 0. And that means that work external is equal to minus Q. So if energy flows in as heat, it flows out as work. If energy flows out as heat, it had to have flowed in as work. So any energy that comes in as work goes out as heat. Any energy that comes in as heat goes out as work. It's more likely that it comes in as work and flows out as heat. That's going to be what's going to be most common. Okay, remember that for an isothermal process, work external is equal to minus nRT, the natural log of V final over V initial. And of course, there's the other ways to calculate it. Okay, and then we're going to meet a new process. Our new process is called an adiabatic process. In an adiabatic process, Q is 0. It's an insulated process, an insulated system, so that no heat flows in or out. Okay? So in an adiabatic process, the change in thermal energy of the system is due totally to external work. Now, just because it's adiabatic and Q is 0 does not mean that delta T is 0. Okay? An adiabatic process, let me draw a picture here and I'm going to show it to you. In an adiabatic process, you get curved lines for the process, just like you did in isotherms. Okay, now let me show you a picture here. My rough sketch. Okay, the dotted lines are two isotherms. If I was going to do an adiabatic compression, I would start out here, point A, and I would end up here at point B. Okay, notice that as we compress, as we're doing work on the system to compress it, we get a increase in temperature, because this would be T1, this would be T2, T1 and T2. T2 is greater than T1. Okay? All right. Make sure I got that lined up. Okay, looks pretty good. Now you can look at the stop and think on page 525. I was just going to ask you some questions about adiabats. Now, thermal properties. We've been concentrating so far in this chapter on gases, but we're going to spend a little time here talking about what happens when we add heat energy in and we're not in the gas phase. We're in the solid phase, we're in the liquid phase. Okay? So, when we add energy into a system, okay, and it's not a gas, either the temperature of the substance changes or the substance undergoes a phase change. So let's run through adding energy to water, starting out with solid water at 50 degrees, or minus 50 degrees C. Okay, now we'll scoot you guys over so you're looking at the board. Well, no, I don't have to do that. All I have to do is change this over to whiteboard. Haha, come on, whiteboard. Okay. Make sure I got a... All right, guys. Temperature here. And added heat energy. So I'm going to put minus 50 here, 0 degrees, 100 degrees. Okay? If I start out at minus 50, as I add heat energy in, the temperature increases. Put some dotted lines in here to kind of help me. Now, in this region, because the temperature is increasing, I know that I have a change in thermal energy. So Qn equals a change in thermal energy. Okay? The thermal energy of the system was increasing. But something interesting happens at 0 degrees C. At 0 degrees C, even as I'm adding energy in, I'll notice that the line flattens out. Here, Qn actually ends up as a change in potential energy of the system. PE for potential energy. I know we usually use Q, but I'm going to use PE here. I mean, we usually use U. But PE will be a little clearer when you come back to look at it. We have a change in potential energy. There's a conformational change. The particles went from being very rigid and locked into position and very close together to moving just a hair further apart and sliding past each other. That means that we popped them out a little bit. We've taken opposite charges and moved them a little bit further apart. That increases the potential energy of the system. And what we see here is solid going to liquid. Okay? Now once everything is melted, then as we add energy in, the temperature increases again. So Qn gives us a change in thermal energy. And once we get to 100 degrees, it flattens out again. Qn gives us a change in potential energy. Temperature remains constant, so the thermal energy content is not changing. That energy that we put in had to go somewhere. It went into potential energy. This amount of energy to go from a liquid to gas is going to be much more than to go from solid to liquid. It's a much larger change. In liquid, from solid to liquid, you're just loosening things up and moving a little bit further apart. Going from liquid to gas, you're taking things that are in contact with each other and moving them light years apart, I mean really far apart. Once you get to everything in the gas phase, then if I add heat energy in, the temperature increases again, and we see a change in thermal energy. Okay, so this is a basic kind of energy transfer diagram. If I'm adding energy in as heat, and I have a nice closed system, what happens? Okay. All right. Now, kind of talk through that. For every substance, then, we can talk about specific heat. Specific heat, lowercase c, is the amount of energy in joules needed to raise the temperature of 1 kilogram of a substance by 1 Kelvin. Sometimes you also see it in energy needed to raise the temperature of 1 gram of a substance by 1 gram of substance by 1 degree C. Okay? So, and I should have a degree K here. I think it moved it screwed it up. Now, here's some specific C, kilogram Kelvin. Now here you see some heat capacities from some solids and some liquids. One of the things I want you to notice that the heat capacity for ice is different than the heat capacity for water. Okay? We'll talk about molar heat capacity in a minute. Notice that the capital C here is the joules per mole Kelvin. So it's the amount of energy to change the temperature of 1 mole of a substance by 1 degree Kelvin. Okay? So different materials have different attractions between the particles, therefore different specific heat capacities. For a solid, the change in thermal energy is calculated as delta E thermal times the mass times the specific heat times the change in temperature. Now this is a plug and chug type problem. We're going to do one in just a sec. Okay? Delta T is the change in temperature, and even though it says degrees K or Kelvin, remember that when you're taking difference in temperature in Kelvin and difference in temperature in Celsius, it's the same thing. So don't take a change in temperature, C, and then add 273 to it. It's wrong. Okay? So we can say if the temperature is changing, change in thermal energy for a solid or a liquid is equal to mass times heat capacity times delta T, which could be from Q plus W. We're working mainly with Q right now. But you could heat something up by stirring it real hard if it was a liquid. If no work is being done, then Q equals change in thermal energy, which is MC delta T. Now, to change the phase of matter requires an input of energy, usually heat, to go from a solid to liquid, and then from a liquid to a gas. Okay? So that brings us to heat of fusion, or latent heat of fusion, L sub S. It's the energy needed to convert 1 kilogram of a substance at the freezing point from solid to liquid. The energy input does not end up, like I said earlier, in thermal energy, but in potential energy. And Q is equal to L sub F times M. Heat of vaporization, L sub V, is the energy needed to convert 1 kilogram of substance at its boiling point from a liquid to a gas. And Q there is equal L sub V times M, the mass, again. So we're going to do a quick problem here. So if I have a hunk of ice at minus 67 degrees C and I want to convert it, oh, hold on a second here. I'm back, guys. Somebody was knocking on my door, and so I had to hop out. So we're going to take a hunk of ice from minus 67 degrees C and convert it to water at 50 degrees C. And then let's take it to water at 100 degrees C and let's evaporate it. No, well, this one says minus 67 up to 50 degrees C. So let's start looking at this. Okay. No, I can leave that. No, over here. Sorry if I'm making you guys dizzy. All right, here we go. So first, we're going to go from minus 67 degrees C ice to 0 degrees C ice. Okay? And let's say that we've got 0.500 kilograms of ice. So the change, well, Q here, to do this, is going to be the mass of the ice times the heat capacity for ice, change in temperature. Well, the mass is 0.500 kilograms. The heat capacity for ice, I'll have to roll this down. It's not something I have memorized, not something I expect you to have memorized. The heat capacity for ice is 2090 joules per kilogram Kelvin. Now the change in temperature, 0 degrees C minus 67, minus 67 gives me 67 degrees C change, which is also a 67 degree Kelvin change. So if we multiply that out, 0.5 times 2090 times 67, we get a Q equal to 7.00 times 10 to the 4 joules. That's how much energy it takes to get it up to ice at 0. Now, if I want to go from ice 0 degrees C to water 0 degrees C, then Q is going to equal the mass, 0.500 kilograms, times the latent heat of fusion for ice. So let me look up that value. On a test, it would be given to you. It's provided in tables in the book. So latent heat of fusion. Come on, latent heat of fusion. For water, it's 3.33 times 10 to the 5 joules per kilogram. Now remember, a joule is a fairly small energy unit, so that's not that out of line. So 0.5 times 3.33 exp5 gives me a Q of 1.67 times 10 to the 5 joules. Now if I want to go from water, 0 degrees C, to water, 50 degrees C, Q is going to equal the mass, 0.500 kilograms, times specific heat capacity for water. And the specific heat capacity for water is 4,190 joules per kilogram Kelvin. And our change in temperature is 50 K. It's a change in temperature of 50 degrees C, which is the same as a change in temperature of 50 degrees K. So 50 times 4,190 times 0.5 gives me a Q here of 1.05 times 10 to the 5 joules. Okay? So if you were given a problem that asks you how much heat energy does it take to go from water at minus 67 degrees C to, ice at minus 67 degrees C to water at 50 degrees C, remember you got to break it up into sections. You got to deal with the warming up, and then the phase change, and then the warming up again. Okay? All right, now let's slide back over. Make sure we're lined up. All right. Get kind of back up here. Now, let me mention calorimetry, because we're going to do a calorimetry experiment as part of our one of our first two experiments in lab. Calorimetry is a process used to measure specific heat capacity and/or thermal energy transfers between two things in an isolated situation. So they're isolated from the rest of the universe. So any heat energy lost by object 1 is going to be gained by object 2, or any heat energy lost by object 2 is going to be gained by object 1. So in a calorimetry problem, mass of object 1 times heat capacity of object 1 times change in temperature of object 1 is going to equal mass of object 2, heat capacity of object 2 times change in temperature of object 2. The key thing to remember in calorimetry is that this thermal energy transfer is going to continue until the two things reach the same temperature. Okay? Once they reach the same temperature, the transfer stops. So let's look at a calorimetry problem. Now guys, if you go to the end of the chapter and we look at page 543, okay, and we look at, let's look at problem 21, which is actually one over. It says that 30 grams of copper pellets, well, here, let me get us over to whiteboard. Come on, whiteboard. Need a whiteboard. Okay. So we got 30 grams of copper pellets, and they've been heated to 300 degrees C. Okay? And they are immediately dropped into 100 milliliters of water at 20 degrees C in an isolated system. I want to know what T final is going to be. Okay? Now, 30 grams is the same as your book always does everything to 3 significant figures, so that's 3.00 times 10 to the minus 2 kilograms. And 100 milliliters of water, density of water is 1, so it's 100 grams. So I have 0.100 kilograms of water. Okay, the heat capacity of copper is something we have to look up. If I look up the heat capacity of copper, come on, give me the heat capacity of copper. The heat capacity of copper is 385 joules per kilogram Kelvin. And the heat capacity for water is 4,190 joules per kilogram Kelvin. Okay, so if I start putting this together, I have 3.00 times 10 to the minus 2 kilograms times 385 joules times T final minus 300 degrees C. I can use it in degrees C because change in temperature Celsius, change in temperature Kelvin can be the same thing. I could also write this as joules per kilogram degrees C. Exact same thing. That has to equal 0.100 kilograms times 4,190 joules per kilogram degrees C, T final minus 20 degrees C. Okay, and there's a negative sign here. So let's start playing with the math. So I have 3 exp2 negative times 385. So I have 11.85, and notice the kilograms and kilograms divide out, joules over degrees C, T final, minus 3,555, and that's going to be, let's see, joules, equals 0.1 times 4,190. So I have a minus 419 joules over degrees C, T final, plus 8,380, and that's joules right there. Now let's combine like terms. 8,380 plus 3,555. I have 1,193, 11,935 joules. And on the other side, I have 430.85 joules over degrees C, T final, divide through, and I get T final to be 27.7 degrees C. If I look at things, your book always solves to 3 significant figures, so I took that to 3 significant figures. Okay, so that's a calorimetry problem. And we'll be doing one of those in lab next week. Okay, so let me erase the whole board. And let's go back. Now, when we have substances in the gas phase, okay, gases are going to behave a bit differently than things in the solid phase or the liquid phase. And we're going to see processes where energy is being transferred in and out as just work, just heat, or a combination of work and heat. So if we think about our processes, isochoric, isobaric, isothermal, and adiabatic. In the isochoric process, okay, which is constant volume, the only way energy moves in and out of the system is by way of heat. Okay? If you're isobaric and isothermal, you have energy moving out and in as both heat and work. And if you're adiabatic, you just have energy moving out as work, no heat. The heat capacity of a gas actually depends on what kind of process the system is undergoing. Is it going a isochoric process? Is it going an isobaric process? Is it going isothermal? Is it going adiabatic? So the 2 most common ways we think about the amount of heat energy moving in and out of the system that we're going to look at are isobaric and isochoric. Now remember that any change in, for us, since we're not doing any macro scale changes to our system, the change in energy of our system is going to be a change in thermal energy of our system, which is equal to work plus heat. And that's where we're going to run into molar specific heat capacity. It's the energy needed to raise the temperature of 1 mole of a substance by 1 Kelvin. For solids and liquids, we really only talk about one way to do that. Gas, there are multiples. Okay, so let's start by looking at isotherms for a minute. Okay, give me back. All points along an isotherm, okay, are at the same temperature, so therefore they're at the same thermal energy. So, blue here. So, blue. Pressure volume diagram here. An isotherm is a line that looks kind of like this. The pressure times the volume are always equal to each other. P1 V1 has to equal P2 V2. Temperature is a constant. If I'm moving along an isotherm, okay, since the temperature is remaining constant, then the thermal energy content of the system is constant. That means if I'm doing an expansion, let's say I'm going from here to here, okay, from this point to this point, as I move along that isotherm, as energy is flowing out as heat, as work, because we're expanding, energy has to be flowing in as heat. And energy flowing in as, so this is where we have work external is equal to minus Q. Because the change in thermal energy is 0. Okay? Now, let's scroll up here. We think about changing from one isotherm to another. There's a change in temperature because there's a change in thermal energy. Okay, so I moved between two different isotherms. No matter which point you start on isotherm 1 and which point you go to in isotherm 2, since the temperature on the two isotherms on all points is the same, you're always going to have the same change in thermal energy. Let me give you a pretty picture here. Book does better pictures than I do. Okay, so here are two isotherms. Isotherm 1, isotherm 2. Isotherm 1 here, the initial is at a lower temperature than isotherm 2. But if I go along trajectory A and I go along trajectory B, it doesn't matter. I have the same change in thermal energy. Okay? Go up here. So, change in thermal energy A is going to equal change in thermal energy from pathway B. But these two pathways are different. A is isochoric and B is isobaric. I know in A, no work is done. So change in thermal energy for A is just equal to Q. Not the same for B. Change in thermal energy for B is actually equal to W plus Q. Here, remember, in A, work external equals 0. Okay? Now, this brings up some interesting points. If I were to put a point C here, and I were to go directly, I would still have the same change in thermal energy. That's not a normal process, but I just wanted to throw that in there. Okay. So the pathway you take to get from one isotherm or another is actually going to affect the molar specific heat capacity of the gas. Because the energy input from work or heat, or a combination thereof, depends on the pathway that you take. Remember, work and heat are pathway dependent. They are not state functions. And the two most important cases for us right now, and then we're going to add on a third, is the isochoric and the isobaric, which we were just looking at. Okay? Isochoric process, isobaric process. So, isotherm 1, isotherm 2, always going to have the same change in thermal energy when you move between them. And I've kind of gone over all this. So, for isochoric process, work is 0, change in thermal energy is equal to Q. So change in thermal energy is going to be in C sub V, V for constant volume. So I have the molar heat capacity under constant volume times change in temperature. Okay? For an isobaric process, work is equal to minus P delta V and is not 0. So the change in thermal energy is equal to work plus Q, or is equal to Q plus a minus P delta V. So in this case, the amount of heat energy to cause the same change in thermal energy is going to be different. So notice it's minus P delta V. So it's actually going to take more energy put in as heat to raise the temperature, or raise the temperature, change the thermal energy content of a system that's undergoing an isobaric process opposed to an isothermal process. Okay? C sub P is the molar specific heat capacity under conditions of constant pressure. So I want to show you this neat little table. It's 19.4 in your book, but this is a table out of an earlier version of the book, and this chapter was chapter 17 in that version of the book. Now, notice there's C sub P and C sub V. C sub P is always going to be larger than C sub V because it always takes more heat energy under constant pressure situations to increase the thermal energy of the system than it does under constant volume, where there's no work done. I want you to also notice that C sub P minus C sub V is always 8.3. Essentially, it's R. The difference between C sub P and C sub V is R, the gas constant. Also notice that monatomic molecules all have essentially the same C sub P and C sub V, and diatomic molecules have C sub P and C sub V's that are very close, almost identical. Diatomics look different than monatomics because of the fact that in diatomics we now have some vibrational motion. In monatomics you can have rotation and you can have translational motion, but there is no vibrational motion as a way to store thermal energy. Okay? So delta is the same for both cases, but Q is different between the two. Capitals are used because we're dealing with molar heat capacities, not dealing with kilograms. So QV is equal to N C sub V delta T for a constant volume process. QP is equal to N, the number of moles of gas particles, C sub P delta V for a constant pressure process. Okay? Since the change in thermal energy between two isotherms is the same no matter what process you get, unless we're interested in the way the energy is distributed, whether it came in as heat or work, okay, we can always calculate delta E thermal based on the isotherms and a constant volume process. So if I'm going between two different temperatures, I can always calculate the change in thermal energy as N C sub V delta T, even if that's not the process I'm undergoing. If I'm not interested in what came in as heat and what came in as work, or left as heat or left as work. Okay? Now, we've talked about the relationship between C sub P and C sub V. C sub P equals C sub V plus R, where R is the gas constant in terms of joules. And lastly, adiabatic process. An adiabatic process is one for which no heat is transferred in or out. Heat is zero. But the temperature of the system is going to change because we're putting energy into the system as work, or we're taking energy out of the system as work. But even for an adiabatic process where there is no heat flow in or out, I can still calculate the change in energy, thermal energy of the system as N C sub V delta T. Okay? But in this case, the change in thermal energy, if I'm interested in where it comes from, is coming from work. So let's look at an adiabatic process. Right, the red dotted lines, those are isotherms. T1 is lower than T2. Now, if I follow this adiabatic process, this is an adiabatic compression. I am putting energy into the system as work. So notice that I pass from this isotherm to this isotherm. So as I'm undergoing an adiabatic compression, we're adding energy into the system, and the temperature is going to increase. How much energy change we see is in C sub V delta T, and that tells us how much work was added in. If I look here, I have an adiabatic expansion. I go from my higher temperature to a lower temperature. That means energy is coming out of my system, okay? I'm going to have a change in thermal energy. All the energy out is work, and I can still calculate it as N C sub V delta T. Along an adiabat, the trajectory for an adiabatic process, the following relationship holds. PV gamma equals a constant. So I could say P1 V1 to the gamma has to equal P2 V2 to the gamma. Now, gamma here for monatomic gases was 1.67, and for diatomic gases it's 1.40. So here's a summary table. It says for an isochoric process, okay, change in volume is 0. So volume is held constant. So that means pressure divided by temperature is constant. Work is going to be 0, and all the energy moving out for the gas is in terms of heat, which is N C sub V delta T. For an isobaric process, change in pressure is 0. So pressure is held constant. Work is minus P delta V, and Q is equal to N C sub P delta T. Remember, C sub P is always greater than C sub V. For an isothermal process, change in temperature is 0. Okay? Change in thermal energy is 0. And work is equal to minus nRT, natural log V final over V initial, which equals the negative of Q. Okay, so I'm just going to quickly add this in here real quick, which equals negative Q. And lastly, for an adiabatic process, Q equals 0, and P1, PV to the gamma stays constant. All of the work goes into changing the thermal energy of the system, and Q is 0. And remember, we can relate this to N C sub V delta T. Now, this is a great summary table for for most of the problems that you're going to encounter in this chapter. Here are some suggested problems for you guys to try. Let's see, let me look at, maybe do one of them with you. Flip here to the end of the chapter. We can look at problem 27. So yeah, we're gonna look at problem 27. Okay, I'm gonna leave that up there. We'll come back to it. We'll kind of keep going back and forth a little. Get us a little working room over here on the board. All right, guys, I'm gonna slide you over this way. All right, we look at problem 27. It says that we have 1 gram of oxygen. And we're at a pressure of 8 atmospheres. And it wants to know Q if the temperature increases by 100 degrees C at constant pressure. I want to find Q when delta T is 100 degrees C and P equals a constant. Okay, that's part A. Now, that means that we're dealing with a isobaric process. So Q is going to equal N C sub P delta T. To get N, I'm going to go 1.00 grams, and 1 mole of oxygen has a mass of essentially 32 grams. That's something I know. If you guys don't know how to get a molar mass, remember on the periodic table, you just, since oxygen is a diatomic molecule, I take its molar mass and multiply by 2, and that's where I get the 32. So 1 divided by 32 is 0.0312 moles of O2. So Q is going to be the 0.03125 moles times the heat capacity, and because that is a diatomic gas, C sub P is going to be, come on, I had it, it's 29.2, and that's joules per mole change in temperature C or change in temperature K, and our change in temperature is 100 degrees C. That'll cancel out. So 0.03125 times 29.2 times 100 says that we need 91.3 joules of energy. Now, I would expect it to be positive because we increased the temperature. If we look at part B of the problem, it says how much will the temperature increase if this amount of heat energy is transferred to the gas at constant volume? Okay, so now I'm dealing with Q is equal to N C sub V delta T. So we're going to go 91, this is part B. 91.3 joules is equal to the 0.03125 moles. And the C sub V for oxygen is 20.9. Joules per mole degree C. Delta T. So 91.3 divided by 0.03125 divided by 20.9 says that the change in temperature is going to be 140 degrees C. You could also say 140 degrees Kelvin or Kelvin, because the change in temperature is the same in C and K. Notice that the amount of energy it took to raise it 100 degrees under constant pressure gives me a 140 degree change at constant volume. That's because, remember, some of the energy we put in under constant pressure ends up going out as work because it's undergoing an expansion. Okay, so that ends chapter 19, guys, and we should be ready then for chapter 20. So 20 is next up on the hit parade.